since TCP uses connections, if you want to work with an application layer protocol like HTTP up to, but not including HTTP 3, if you want to work with something like HTTP 1.1, HTTP 2, you need a TCP connection. And if you want to do socket programming with TCP connections, it's a little bit more involved than UDP, but that just means that you need to make a couple of different, or you need to be familiar with a couple of different system calls. So that's the ultimate objective of this exercise, to expose you to those system calls. But in order to do that, what you're going to do is write a program which is a little HTTP server. So it's going to receive HTTP requests from the browser or from curl or whatever, and it should parse the headers in that request and reformat them in JSON and just serve them back as a valid HTTP response. All right, but obviously I want you to use the socket system calls or whatever is the lowest level interface that you have in your language for doing that. So you'll need to listen for connections. You need to indicate to the operating system that you're ready to receive connections. And then you need to repeatedly accept connections. Each time accept returns, you'll have a new connection from the browser or curl or wherever. And you need to do the thing and then be ready to accept another connection, basically. You're a server. Your lot in life is to, in a loop, just wait for connections. Well, you're a TCP server. Your lot in life is to wait for connections. If you're a UDP server, you just wait for messages. Okay. It should be a fairly straightforward and short exercise. Hey, maybe you want to extend it and have some fun and hit some stretch goals, but this is the core objective. Receive an HTTP request, return a valid HTTP response. I will go ahead and solve it as well, as usual. If you want to follow along with me, the first step that I will take is to write basically a TCP echo server. So before I tackle any of the HTTP specific stuff, I just want to make sure I've got this basic loop where if someone opens establishes a TCP connection with my program and sends a message, I'll just echo it back so that I know that I've got the core mechanism in place. All right, so either go ahead and implement the whole thing, or maybe aim for that first goal that I'll aim for now. All right, so I'm going to attack this in two phases. The first one won't have anything to do with HTTP. It'll just be to get the core TCP loop going, and then I'll do the HTTP specific stuff subsequently. I feel like it's worth thinking about how you decompose the responsibilities of the program, even if your code ends up incorporating the responsibilities, just so you can have clear milestones. And hey, maybe it makes sense to separate your code in the same way as you separate your milestones. Anyway, so we just want a server here, and the goal for this step is accept a connection, echo back anything received. Okay. So we'll need a socket. It's going to be an internet socket. And it will be a streaming socket because we're accepting stream. Because we're accepting TCP connections, so that's a streaming socket. Now, where do we accept the connection? We're going to have to bind. I'll bind to any address, ports, make it up. With TCP, there are two steps to start accepting connections. First, you need to indicate to the operating system that you are able to accept connections. You're ready and willing to accept connections, and then you're going to accept connections. And if it's a server, you're going to want to do this repeatedly. I guess technically, for our goal, we're only trying to accept one connection, but we'll get ready to accept more than one. So let's see if we're going to accept connections now, we're going to call connect. Again, in Python, these are methods on the socket object. For you, maybe they're functions, maybe you're using the system calls directly. Sorry, I'm not trying to connect this to... Connect is what you would use if you were trying to establish a connection to somewhere else. what we're trying to do here is accept new connections. And accept is going to return both the connection, which is another socket. So here we have a socket that we're using to communicate with the operating system about our willingness to accept new connections. And as those connections come in, each one is a new socket. Why would you want this? Well, because once you get into a more sophisticated kind of scenario, imagine you are really a web server. You don't want to be blocked working on the one connection that you've accepted right now. You want to be able to accept a lot of connections and do a lot of work in parallel. Or if not in parallel, then at least concurrently. Even if you've only got one CPU core, you don't want to be blocked, waiting on a database query or something for one connection and not be able to serve another connection. You also don't want to be blocked working on one connection and not be able to receive new connections. So that's what this other socket is for. So the actual mechanism for being able to do this concurrently we'll get into later. But for now, if you want to understand why this is one socket and then we get new sockets for connection, well, that's the reason to distinguish those things. Okay, so accept returns a connection and the address of the party with whom we have this new connection. So we have this connection now. We should be able to receive from it. Obviously, we are we're calling this on the connection socket, not the socket that we use to receive the connection, which we called S. So we're going to receive. We need to say the maximum size. I'll just make it a large number. Doesn't really matter. Well, it doesn't really matter if it's large enough. If it's small, that's the extent of the data you're going to get, and you're going to have to re-invoke receive. Okay, so now that we have this data, let's actually do it this way. For the one connection, let's keep receiving data so that we can keep having this chat. If we have data, that is to say the other side hasn't closed its connection, and so receive hasn't come back empty, then we're going to send it back. That's it. Receive is going to give us bytes. Send expects us to send bytes. So echoing back like this should be fine. And then at the end, well, the connection is going to be closed by the other party. All right. So this is fine. I guess we should just say for completeness. Okay, and let's see. I'll give myself some feedback about what's happening, just in case this doesn't work first try. So let's say here, let's print out listening. Let's do this. Listening for new connections on port. Okay, and here I can say print new connection from this address, and here, oh, I forgot to break. I'll just do this, if not data, break. That would have been a bug. Not data break, otherwise echo it back. All right, so do I want to print data? Yes, I'll just say this. It's going to print that as bytes. That should be fine. All right, so let's give this a try. We'll run it. Listening. So we should be able to open Netcat. Let's do this. Maybe I'll do this on the left and the right. So on the left, I'm going to have the client, and the right is our server that we just wrote. And so we'll need to connect to localhost 7777. Okay, when I hit enter, I should see on the right-hand side, received a new connection from some random port that Netcat gets assigned. Okay, so we do have this new connection, and now I should be able to type hello and press enter. And by pressing enter, that Netcat sends that packet. And so I should see here output that there was hello, and I should see back here hello again because we're echoing back. All right, hopefully that works. Yes. All right. And we're still in the loop in the server. It hasn't broken, so I should be able to do something again. So that works. If I SIGINT, if I terminate the Netcat process, in cleanly handling that interrupt, Netcat will close the connection. That will cause the operating system that's managing the socket to allow receive to return, but return with no data. So that will mean that, hopefully if this all works, this is kind of the edges, but you should still be careful about how your program works at the edges, obviously. That will, the way that we coded that up, that means that receive receives no data, data is empty, and so we break out of the while loop that's trying to echo back from this connection, we close that connection, and we're ready for a new connection. So I should be able to SIGINT here, this process stays alive, open up Netcat again, it'll be on a new port, new connection, and it'll still work. So SIGIN, I guess we're printing it either way, that's fine. So let's make a new connection. Netcat, received a new connection, new port, and this all works, and it continues to work in a loop. All right, so that's it. It works as I intended. Obviously, there's no HTTP here. We've got TCP, and we're just sending words. We're just sending bytes and echoing them back. Really, we want to use our TCP connection for something interesting, right? You want an SSH into another machine, or you want to send an email, or you want to do HTTP. You want to make an HTTP request and get back a web page. So that's the application of application layer protocols like HTTP. So that'll be the next step. Now that we've got the basic mechanism in place, we've got the right system calls. Now we're going to do the HTTP specific stuff of parsing the request that comes in and sending back a response. So you'll have to know a little bit about HTTP already in order to be able to do this, but maybe you're a web developer or something, you've got some exposure to this. HTTP is a pretty straightforward protocol. So I'd say go ahead and do this step now if you're ready. Otherwise, follow along with me. I'm really just going to receive the HTTP request, parse it, get the headers. I'm going to do a quick and dirty thing. It won't be a really robust parser, and just send back the response. This should hopefully be straightforward too, although we may run into some of the edges of HTTP. Let's see. So basically, we want to now treat whatever's coming over the TCP connection as HTTP. Assume that it's an HTTP request. We will parse the headers, format them as JSON, and then send back a valid HTTP response with that JSON. Okay. So data here, now I'll just call this request, right? Because we're just assuming it's a valid HTTP request. You could validate that it is formed correctly, that the request line is correct, and so on. I'll just assume that it's all good. Another thing that I'll assume is that this is the entirety of the request. Now, really, what you should do, in fact, I'll make this a to-do, and you could see this as a stretch goal. You should keep calling receive, because there's no guarantee that the entire request shows up in one fell swoop. It may be sent in more than one packet, just because that's how the client was implemented, or because there's so much data. Imagine a ton of headers, or imagine a post request with a lot of data in the body. May not fit in one network packet, which is typically around 1500 bytes. So you would have to keep calling receive over and over again in order to get the entire request. Now, why is this? Why am I not going to bother to do this now and just tell you that it's a stretch goal for you? Well, when do you stop calling receive? When should you stop calling receive? Like, how do you know that you've got the whole request? In some cases, it's straightforward. If the other side closes the connection, like we see in curl, it just makes the request and closes the connection, or Netcat. then, well, not Netcat actually. Netcat keeps it open so you can keep typing, but curl would close the connection. If they close the connection, then you're going to, as you loop through, see that there's no data coming through, and you know that that's the end. That is to say, the operating system returns receive, but with no data, and so that's the end. The connection is closed. But a modern browser is not going to close the connection. It wants to maintain the connection so that it can request HTML, say, parse the HTML, and then it can request the CSS and so on, and not have to establish a new connection over and over again. So it's not going to close the connection. Well, how do you know when the request is finished then, and it's time for you to send a response? It's kind of like you're trying to have a conversation with somebody. You need to know when they've stopped talking so that you can start talking. So with a GET request, that's straightforward as well, because there's no body, and so you can just keep listening until there are no more headers. But what about a POST request? Well, then you'd need the content length in order to know the end. Anyway, all this is to say it's a little bit complicated to do this the right way. The right way would be to keep calling receive and figure out when you've got the end of the data. Maybe it'd be interesting if you want to understand HTTP. This would be a small aspect of doing that. All right, I'm not going to do that though. I'm going to call receive one time, assume that that's my entire request. I won't print it out. I'm going to send back the JSON encoded form of the headers. I'll leave this out for now and actually do that work first. So I have the request. How do I parse the request? Well, this is going to break in many cases, but by and large, the headers and body of an HTTP request are separated by, do you know what this is? Are you a web developer? You know these details? The 4-byte sequence, carriage return new line, carriage return new line. Right? Due to the legacy of teletype machines that come from typewriters, where the carriage moving to the start of the existing line, returning to the start of the existing line, is different to the line feed, the paper moving through anyway. So officially it's this. You should, though, be permissive, and if someone just sends you line feed, you know, /n/n, then you should treat that the same way. We're not going to do that. We'll break in many cases. You know, you should, like, if nothing else, you should catch the exception here and keep looping so that someone can't just crash your server by sending a malform request. But look, I'm just going to tell you that and then continue so we can focus on getting this done. Stretch goal. Okay, so there are hopefully our headers and body. Now we'll ignore the body. If on a GET request, this body thing should come back as an empty string, and on POST request, we'll just ignore the entire body. Okay, so now let's process the headers. We're going to set up a Python dictionary here, and we'll say for header line in. Now, how do we parse the headers? Again, this could break, but if we say headers dot split, how are two headers separated from one another? Well, visually, it's like on the next line, but we don't care about visually here. That's kind of from the legacy of HTTP. We need to know what to split on, what byte sequence to split on, and it turns out to be specifically the carriage return new line byte sequence. Now, again, you should be permissive, but officially, the request is meant to separate headers by the 2-byte sequence carriage return new line. All right, so let's just assume it's like that, and you know, it's not going to work if stretch goal. So, hey, the point is for you to do the work here, not me. Let's ignore the request line as well, because that's going to be something like get /HTTP 1.1 or something. Again, you could validate that stretch goal. You could validate that, but I'm not going to. I'm just going to discard it. Okay, so these are the actual header lines that we're working with here, and the key and value we're going to derive from splitting. Look, this is the worst HTTP parser you could imagine. We don't want to construct all these different byte sequences and use split over and over again. Ideally, you want to scan through the data as it's coming in, even before you've received all of it, one time sequentially, and do work as you get more and more data. And so you want to say, okay, scan, 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 scan. Okay, now I have this header. It is content length, and so now pay attention to that to know when the request is fully received. Or it's not content length, we'll just put it in a dictionary now and keep going. The splitting is not the way to do it. Stretch goal. So I will split on the byte sequence, colon, space. Again, you should be permissive. Does it necessarily need to be a space? I actually don't know if it's in the spec or not to have a space. If you're implementing a server, this is Postel's law, you should be permissive. All right. Hopefully that's right. We can put a key in here corresponding to a value. Our dictionary should now be populated with the header key value pairs, so we can send them back. Before we send back the body of our HTTP response, we need to send back a basic response line. So let's first send the byte sequence HTTP 1.1. So ignored what protocol you've requested. We're just going to send back 1.1 and the status code and the status message. Okay. Now, to separate the response line from the body, we don't really need to send back any headers, right? You could send back a content type or something, but typically the headers would come on the next line. Right? But if there's an empty line, then we can send the response, the body, what's called the NC body in the spec. Okay, so this means that the next thing that we send is going to be the NC body. Now, notice here that I'm just calling send twice out of laziness. I could build up a string and send it all at once, but sending twice, sending this as one thing and the body as the next thing, that should also work. It should also get to the other side, and they should be calling receive repeatedly, not just one time like I'm doing, and receive the entire thing. So it is important to keep receiving until you have the whole message. Okay, but I won't bother with that. JSON dot here I need to encode this as a byte sequence. Wait, sorry. I first need to dump to string the dictionary D. Then that thing, which is a string, I need to actually be bytes. So let's do this as, let's just do it as ASCII. Right, because it's the headers, they should just be keys and values in ASCII, no special encode. Okay, that's it, I think. Oh, I need to import JSON. Let me have a think about what else. With this, I can format it. Okay, is JSON going to handle key and value being bytes? I'm actually not sure about that, but it's definitely, I mean, I think it might assume that they're strings, and maybe you can well, probably can't handle them being bytes actually if I think about it, because how does it know what, like, would it just assume that they're ASCII? Let's just decode them from strings. So 2 strings from ASCII. Oh yeah, if nothing else, Python requires the key to be a string. The key can't be bytes of the dictionary, I don't think. Maybe it can actually. It just needs to be hashable. Alright, so Python's fine, but JSON probably won't be. Alright. Look, if you're wondering whether I do these unscripted and just try and get it right the first time, I do these unscripted and try and get them right the first time. So it means I don't know everything off the top of my head. That's fine. Hopefully this works. If not, it may be interesting to watch me debug. So populate this dictionary. Again, we're making a lot of assumptions about the request being well formed. We should just catch all exceptions and keep looping, if nothing else, so that no one can crash our server. But basic idea is here. Let's give it a try. Okay, so running the server, listing for new connections. I could use netcat again and write the request myself with the headers and so on, but I might as well use a program that does that for me, such as curl. So curl will make an HTTP request, make it to this port, and well, I don't think we're printing the data anymore, so we won't see anything here other than new connection from localhost, some random port that curl gets assigned. And here we should see JSON response with the stuff, with the headers that curl sends. Let's see. Drat. Okay. What 80? That's because I need to do this. It's a different interface between netcat and curl. Hey, that's it. Okay, let's try again just to make sure that we don't, the server's correctly looping. Okay, that was a new connection and the same response. Curl sends very nice compact headers, doesn't it? Just like the host, which is technically required in HTTP 1.1, even though it's kind of useless here. And the user agent is correct, kind of shockingly, compared to what a browser does. All right, speaking of browsers, let's try this in a browser. Okay, so where's the server running? Left-hand side, let's try this as localhost 7777. Hey, okay. That looks pretty good. It's kind of funny that we got we got two connections. I don't know if there's a kind of, I don't know what Chrome is doing there, but whatever it's doing, maybe it's making a request in advance for some reason. I don't know. Anyway, one of these two connections gave us a set of headers which are, we've sent back as this. And hey, did I say the browser curl is a lot better behaved than this? Anyway, that's maybe something for another time. Cool. I think we've achieved what we want, primarily exposing you to those socket system calls. So the HTTP stuff is just a bit of a bonus. But hey, if you're a web developer, you should know that kind of thing too.